Hello, so in this lesson we're going to go over topic 1.2 of Calculus AB and BC, and this is going over the definition of limits and how to use limit notation. So something to think about as we're going through this lesson is reasoning with definitions, theorems, and properties can be used to justify claims about limits. So we're going to be learning some new definitions, some new theorems and properties along the way. So we're going to see how that can fit in with limits and what the limits are. So the learning objective for this lesson is to represent limits analytically using correct notation and to interpret limits expressed in analytic notation. So we're looking at a lot about notation of limits and being able to understand kind of where limits come from. So in order to understand where limits come from, we have to look at where does calculus come from, because limits are kind of our tool in order, it's like our key to unlocking all the mysteries of calculus. Okay, that's not quite an exaggeration, but a little bit. But really, there's two main problems that mathematicians were thinking about and trying to solve when they came up with calculus. So the first problem we've discussed already when it comes to rate of change, and specifically instantaneous rate of change. So when you have a function like you see here, where it is curved, it's not a straight line. So at any given point in time along this curve, it's going to have a different rate of change or a different slope. So the problem was, how do we determine what is the slope of the tangent line? So that was the first major problem that calculus had to solve. And the second one was, how do we determine area under a curve? So we pretty quickly were able to determine area of things that were, squares, rectangles, triangles. We were able to kind of calculate the area in that way. However, when it comes to circles or just any kind of irregular type of curve, finding the area underneath that became a challenge, and it was something that mathematicians wanted to figure out. So in comes calculus. And in order to kind of wrap their minds around how this all works, we need to talk a little bit about the tangent line and define it. So we've done this already in class. We know that the tangent line is the line that goes through a curve at one specific point here. So we see it going through the circle, and then we can also see on this blue curve, the tangent line is this line right here. Because it is going through only one point, and because it's following the slope of the curve. Notice you have all the other lines, L1, L2, L3, they only touch the curve at one point. However, they don't follow the slope at that point of the curve. So those are not considered tangent lines. Only that red, now orange line is our tangent line. So we know what a tangent line is. Let's talk about the difference between a tangent and a secant line. So a secant line is a line that is formed by taking any 2 points of the curve. So we see here, L1 is a secant line because of those 2 points. We see L2 is also a secant line because of those 2 points. And then L3 is a secant line because of those 2 points there. And LT is our tangent line because it's only going through the curve once. So how do these relate? Well, when it comes to finding the slope of the secant line, we can see the formula here. Slope of the secant line is equal to f of x minus f of c divided by x minus c. This is our basic slope formula. It's the one you've learned and have used for several years now. So how do we transform it into the tangent line? Well, if you look at our image here, and let's actually kind of work backwards. Our goal is to find the slope of the tangent line. And so if you notice here, we can take a line by picking another point on the curve, and this creates a secant line. However, does this have a similar slope to the tangent line? Not quite, right? But if I pick a point, say that point right there, that is now closer to the point where the tangent line is, and I draw the secant line, we can see that the line is now just a little bit closer to the tangent line. And if I pick another point, take this point right here, and that's our tangent line point, and I draw a line connecting those 2 points, we see now that blue line is getting closer to the tangent line. So what can we assume from this pattern? We can start to assume that the closer we get to this point here, the closer we can create secant line that is close to that point, the closer it will be to becoming the tangent line. So that means that when we are writing our slope formula for the secant line, if our point is traveling closer and closer and closer, what is also traveling is the x value of those points. So what we are saying is that the x values of each of those points, we want them to approach the specific x value of the point where we want the tangent line to be. So in this case, we call it C. So the distance from one point to the tangent line point, eventually we would want it to get so small that that distance here becomes, well, that C value, right? So the limit as x approaches C represents that point approaching that C value. So we have the same formula here, that is the slope formula of a secant line, but we are saying that the secant line must approach that C value. So we have a fun little did you know here. You can check that out to see the meaning of tangent and secant. And now we're going to talk about what is the limit and how does this notation work. So we have the notation, the limit as x approaches a of f of x is equal to L. And we say it just the way that I said it right now. So we read going from limit to x approaching a of f of x equal to L. And what this is saying is, if we have a function f of x here, what we are looking for is this value a, this x value of a, which is a point here on the graph, and we're trying to basically figure out what is that height of that point. And sometimes there may not even be a point. A limit can be a hole, because it's really just estimating what is the value there, what is the height at that specific point. Let's see if I can, looks like I can't open this applet. So if you want to take a look and click at that applet link, it's a fun little kind of graphic where you can see how the limits change there. So we're going to just jump into some examples here, and hopefully that will help us to visualize and see as well what does a limit actually mean. So we're going to start with a graphical approach, and you can see here we have 4 different approaches that we can actually solve this problem. So we're going to do all of them because they're all important. So we'll start graphically. We have the limit as x approaches 3 of f of x plus 2, sorry. So x plus 2 is our function. So what I'm going to do is I'm going to graph this function. This is just the line, the diagonal line, shifted up 2 with a slope of 1. So we've got that intercept there, and it's a slope of 1. So we can just go up 1 over 1, up 1 over 1. We can go down 1 over 1. And that gives us our line. Sorry, it's not, the dots aren't perfectly lined up, but that's okay. So there's our x plus 2 graph. Now what we want to find is the limit as x approaches 3. So you want to think about if you are kind of traveling along this function x plus 2, what is going to be the height as you are approaching the x value of 3? So the x value of 3 is right over here. This is x equal to 3. So if we are kind of tracing this graph and we stop once we are reaching the limit of x equal to 3, I want to take note of what is the height there. And so I can see from my graph, this is 1, 2, 3, 4, 5. So based on the graph, I can determine that the limit as x approaches 3 of x plus 2 is equal to 5. So you may be asking yourself, well, what is the difference between finding the limit and just figuring out what is f of 3, right? Because if you were trying to figure out f of 3, all you would have to do is plug in 3 and you get the y value. Well, limits aren't always necessarily points. So it's possible, in this case, it was possible that maybe we had a hole here. However, if you think about it, the slope at that hole in that function, right, is going to be the same as we inch closer and closer and closer. So with the line, it's kind of obvious. It's kind of like, duh, okay, why are we doing all of this work for this? I can draw a little curve and we can kind of imagine what I'm trying to explain here, right? If we had a hole there and we wanted to figure out what is the slope of the curve at that specific point, and it's a hole, right? But if we were to draw a secant line that was sufficiently close to that point that we're trying to find, right, as it's approaching, it's getting closer and closer to that tangent line point, notice how the secant line is still, whoops, drop that there. The secant line is still very close to that tangent line. So we still want to be able to find that value here for the limit in order to then, be able to talk about slope. So we started with a basic line just to kind of get the idea and the visual here of how to do it. Of course, we'll get into some more complicated problems. Now let's take a look numerically how we would figure this out. So limits are all about patterns, right? We're trying to see what are the patterns of the function so that then we can try to predict what is happening in that function. So numerically would mean we can have a table and fill out some values here. So the limit we are trying to determine is the limit as x approaches 3. So what I'm going to do is I'm going to have 3 in the middle here. And I want to plug in values to the left and to the right of 3 that are very, very, very close to 3, but not exactly 3. So for example, to the left of 3, we may have 2.9, and we may have 2.99, and we may have 2.999. So those are all getting really, 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 really close to 3 on the left side of 3. On the right side of 3, maybe we have 3.001, 3.01, and 3.1. So I chose those points because those are really, really close to 3. And what we want to do is we want to notice the patterns of the points that are really, really close to 3. So if I take 2.9 and I plug that into my f of x, which in this case is x plus 2, I'm going to get 4.9. If I plug in 2.99, I get 4.99. And then I get 4.999. I'm going to skip over 3 and jump over to 3.001. That's going to give me 5.001. And then I get 5.01 and 5.1. Do we see a pattern? Hopefully we see a pattern. And we see that as our x values are approaching 3, on both sides, we see that they're both approaching the 3. Our y values are approaching a certain number as well. Notice on the left, it's getting closer to 5. And on the right, it's also getting closer to 5. So we can see here, even if we didn't know what the value of 3 was, if for some reason we weren't able to plug it into the function, we can make the assumption, we can make that guess that f of 3 would be 5. So the limit as x approaches 3 is 5. And the reason if we didn't have this function, we wouldn't be able to say f of 3 is equal to 5 is because we don't know, maybe there was a hole there, right? Sometimes that may happen, there's a hole. So we can't say f of 3 is equal to 5, but we can say the limit as x approaches 3 is 5 because that's what all the values are showing, that it's approaching some kind of value, right? You can imagine you're taking a road trip, right? And you're following the signs that say you are headed to, I don't know, Los Angeles, right? So you're on the road and all the signs are saying you're 20 miles from Los Angeles, you're 15 miles from Los Angeles, right? And then imagine you've traveled that far and then all of a sudden it says you have reached New York. It's like, that doesn't make sense. All of the signs are leading to Los Angeles. So hopefully that analogy kind of helps out a little. Now, symbolically or analytically, we're going to look at different strategies on how to do that. In the most simplest form, if we were to find the limit analytically, which means with the formulas, your method to solve right away is substitution. Okay. So we're going to substitute this 3 into the equation, and that gives us 3 plus 2, which is 5. And verbally, we would say the limit of x plus 2 as x approaches 3 is equal to 5. We can also say that the value of the function f of x equal to x plus 2 can be made as close as we please to 5, So that means that this function we know is going to get really, really close to 5 by choosing x sufficiently close to but not equal to 3. So technically when we're talking about limits, we're just making assumptions about everything that is close to that value, but not necessarily what's going on at 3, right? Because there could be a point at 3, there could be a hole, we don't know. We're just looking at what is going on as we're approaching it. So let's look at another example. This one is not a line. We have a rational function. G of x is equal to x squared minus x minus 6 divided by x minus 3. So if I were to graph this out, I would need to, first of all, factor this just to make sure and see if we have any holes. So this will be 3 and 2. We want a minus 3, positive 2, all over x minus 3. So I just factored that g of x. And then notice that cancels out. So what does that leave me with? X plus 2. Tricked ya, it's actually a line with a hole in it. So we have the line x plus 2, and we know that x cannot equal negative 3. There's a hole at negative 3. Sorry, not negative 3, positive 3. Okay. So I'm going to go ahead and graph this out. So it's basically the same line that we just had. And we just have a hole at x equal to 3. So if that's 3, then we know that it's going to have a hole. Sorry, I don't know why this, there we go. Right up there. That's a hole, people. Sorry if it doesn't really look like it. There we go. Okay. And just gotta make sure my laptop doesn't die on me. Sorry. So what we're going to do now is we're going to check graphically. As we see these x values approaching 3, what are their corresponding y values doing, or their corresponding points? What y value are they approaching? And we see here it's approaching 5. So we know that the limit as x approaches 3 of x squared minus x minus 6 over x minus 3 is equal to 5. So in this example, we see what we were talking about earlier. We actually have a hole there. So we know that if this is a function g, g of 3 actually doesn't exist, right? It's undefined. So our limit still exists because we can see that all the points near x equal to 3 are all leading up to 5. And we'll prove this numerically by taking our table here and taking points that are really, really close to 3. So we'll have 3 in the middle here, and we'll have 2.999, 2.99, and let's do 2.9. And we can do 3.001, 2.01, and 3.1. Now from here, of course, you would want to then just plug into your function here. Since we simplified it, we know it's going to simplify to this line x plus 2. So it's going to be 4.9, 4.99, 4.999, 5.001, 5.01, and 5.1. And so what do we notice? We notice As the x values are getting closer and closer to 3, there's a pattern with the y values. Those y values are getting closer and closer to 5. So this tells us that our limit is 5 as x approaches 3, even though this is undefined, right? Because if I were to plug that into g, it would be undefined. I would get 0 in the denominator, but our limit is still equal to 5. So I can say here, the limit whoops, sorry about that. There we go. The limit of g of x as x approaches 3 is 5. So that's how we would read that. And now, analytically, with our function, we have the limit as x approaches 3 of x squared minus x minus 6 all over x minus 3. So we said in the earlier problem that we would do direct substitution, meaning we take this 3 and plug it into all of our x's. Well, we run into a problem here because we end up with a 0, which makes this undefined, right? So that does nothing for us when it comes to finding the limit, because we know the limit still exists because the function is still headed in some direction. So we need to factor and simplify just like we did when it came to graphing the function. So when we factor, like we did earlier, these x minus 3's cancel out. So we're left with the limit as x approaches 3 of x plus 2. And now we try direct substitution again. So now that we factored, plug in 3, we get 3 plus 2, and that's 5. So there's our limit. So we're going to do a couple more problems here. It says the graph of the function f is shown below. What is the limit as x approaches 2 of f of x? So we're going to practice our skills with the graphs and analyzing it to find the limit. And since it's asking us for the limit as x approaches 2, I'm going to first determine where x is 2 on the number line, so right there. And then I'm going to check to see what is the graph doing there. So there's two things that are happening. We see that the connected graph here, the continuous, almost continuous part, has a hole in it. And then we have a point there. So if the question were asking you, what is f of 2? We would all say f of 2 is equal to 1. But that's not what the question is asking you. The question is asking you, what is the limit as x approaches 2? So, of this function, right? And so what is happening? This function, if I were to follow along this function on this side, as I follow along, what are all the y values doing? They're approaching that section right there. And same thing on the other side, all of these points are headed in a direction. They're headed right towards that hole there. So our limit is actually what is based off of that function. So this point down here is actually disconnected from the limit. We're actually trying to follow the pattern of the graph. And so the graph is leading us to a y value of 2. So the limit as x approaches 2 of f of x is actually 2. You see our little Mean Girls meme here. We're going to see some examples where the limit does not exist very soon, but that is not the answer today. Next, we're going to challenge our skills looking and analyzing tables. So we want to know, of the following tables, which one reflects the statement, the limit as x approaches 9 of g of x is equal to 5. So what we want is for the x values up top to be approaching 9. So if I look at this first part A, take a look at the x values. They're all approaching what looks like 5. So that's not going to help us. Now we're left with the next 3 options, because if you look here, that x part in all of these, they're all approaching 9, which is good. That's what we want. Now what we want is for the y values to be approaching 5. So if we look here, we want to pay close attention to the patterns. We've got 4.925, 4.950, 4.975, 4.995. Those are all getting pretty close to 5. And same thing on the right, we can see that they're getting pretty close, right, to 5. If we look at the next table, we see 4.95, 4.67, 4.983, 4.997. So those are all approaching 5 on this side. But if we look on the other side of 9, notice how these y values are all approaching 10. So we've got 5 on one side and 10 on the other side. That's not going to work out. We need our limits to be approaching the same from both sides. So this table, C, is not going to work for us. Now if we look at D, we start at 6.667, and then we're going to 10 and 20 and 100. These are getting significantly larger and higher. So this is telling me that this is actually approaching positive infinity. All those y values are getting bigger and bigger. And on the other side, these y values are actually getting further away from 5. It looks like it's getting closer and closer to about 4.5, right? Maybe headed towards 4. So both of those are not getting close to 5 or approaching 5. So our correct answer for this problem will have to be B, because we can see very closely that on both sides, both of the y values are all approaching 5. Now here's our last problem. It says, let f be a function that is defined for all real numbers x. And of the following, which is the best interpretation of the statement, the limit as x approaches 2 of f of x is equal to 7? So when we're talking about limits, we're not talking about values. Values are when we actually plug in the values, right? So if it was written as f of 2 equal to 7, that would be giving us the value of the function. However, it's a limit, so neither of those will work for us. Now we see here, as x approaches 2, the values of f of x approach 7. So we're still talking about the values of f of x, but they're approaching a value rather than actually being equal to a value. So that's more of a limit there. And so it is approaching 7, which is what we have here. X approaches 2 is what we have here. So C is the correct answer in this case. And that concludes our video on Introduction to Limits.